Hello, everybody, and welcome to yet again another recorded Zoom interview. And back by popular demand, Dr. Cameron Davidson from Carleton College in southern Minnesota. Cam, the weather today on another Wednesday in October. What is it like over there?
Well, it's finally feeling like October. It's a high of 52 today and cloudy, and there are still puddles on the ground. But it's
Okay,
supposed to warm up this weekend, so we'll see.
that sounds familiar. Very good.
Yeah.
Well, viewers, this is part two, essentially. A week ago, Cam and I were talking about the Chugach Terrane, the Prince William Terrane, getting just some basic ideas going for me and maybe many of you out there. But there was plenty that Cam had to share with us. And so as we were talking last week, I said, well, I think we should do a part two, and here we are. So, Cam, can we go back to the basics, maybe a little recap of what we did the first time with what kind of major stories do we have in the Chugach Terrane? And then how is today going to be different, do you think?
Yeah, so the plan was we mainly talked about some of the geologic evidence in the Chugach Prince William terrain and the Yakutat terrain for large-scale coastwise translation.
Yeah,
And that was mainly doing detrital zircon work and showing some comparisons with the Pacific Northwest. Well, and also just sort of what is the Chugach terrain, a little
right.
bit of that. But then today I thought it'd be fun. Well, and you asked, I said, well, what about the Sanic Baranoff plutons? They intrude the Chugach Prince William terrain, and we've been working on that as well. And we've had a number of students, I think it's over 40 students that have been working on this stuff.
Mm,
And over the 12 years we've been doing it.
yeah.
And so we thought, well, let's talk about that too, because it's a cool part of the story, it turns out.
How about one thing from me before we go to the slides? You mentioned there was just an incredible amount of turbidite bedrock in the Chugach. How do you know it's turbidite? Are there any other interpretations of those alternating sandstones and shales?
Not that I know of. I think, because of the sedimentary structures that you see in them, beautiful graded beds, flute casts, rip-up clasts, or whatever
Yeah.
sedimentologists are calling those now.
Okay.
It's just sands and shales stacked on top of one another. And really the best explanation for that is some sort of alluvial fan, continental sedimentation emptying out into the trench. And in this case, as soon as they reach the trench, they get incorporated into the accretionary wedge.
I see.
I have a picture of sort of showing that model that I thought would be helpful.
And there's any telltale signs it's marine? There are marine fossils
There
or
are
any?
there are few. I mean, that's one of the
Mhm.
problems with turbidites. There are a few marine fossils,
Yeah,
and that's how people figured out there are probably Cretaceous and even some Paleocene in there.
I see.
But they're few and far between. And so
Nice.
that's why we did the detrital zircon work to try to really nail down what those ages might be.
Good. Well, today, to start with, viewers, we're going to have magmas come up through a bunch of that turbidite material, and there's a story with the magmas about why the magmas are coming up, where they're coming up, and they're not all the same age. So let's go ahead and share your screen, Cam, if we can do that, and get off of that beautiful, sexy, fuzzy background you got there in
Yeah,
your office.
I know.
I love
I'll
it.
figure
I
it out
love it.
eventually, I guess. Okay, so share
Very good.
my whole
Okay.
screen. There we go.
And we forgot to practice. There we go. Good. We'll
Yeah.
start with John Garber. Excellent.
Yeah, I forgot to really emphasize this last time, and so I wanted to do it right away up front. So
Good.
John and I have been working on this for, like I said, the last 12, 15 years, and it's really been truly a joint project. So I just wanted to acknowledge John and all of his contributions. He's been a lot of the inspiration for this, to be honest. So
Excellent.
just wanted to acknowledge him. And just to remind some viewers, or remind us all, where is the Chugach Prince William terrain? I showed this last week. This is that terrain map of Alaska. Oh, and let me turn on my pointer.
Excellent.
So there we go. And so you can see here in, I guess that's light brown, labeled CH. That's the Chugach and Prince William terrain. Here's the Yakutat terrain.
Hmm.
Chugach comes all the way down here to Baranoff Island in Southeast Alaska as well. And so it's mainly this area that I'm going to focus on. And where was that at different times, as well as the Yakutat terrain.
Thank
And
you.
what I tried to make the case last time is that this originated down here in Pacific Northwest. And what I'll try to show you today near the end is that we also think it came all the way from Southern California at one point to the
Okay.
Pacific Northwest and then to where we find it today.
Nice.
So what is the Chugach Prince William Terrane? Well, most people interpret it as a accretionary wedge complex. So here's a simple cartoon of, a continental arc. And so here's the accretionary wedge out in front, just to remind people, downgoing lithosphere. And the reason I like to point this out is that, this is where the arc is, the modern arc in a typical accretionary prism. And so where are the plutons? Well, you'd expect them to be over here, some, 150 to 100 kilometers from the trench, from where the
Yes.
accretionary prism is. But in the Chugach, we find plutons intruding into the accretionary prism. So
Huh.
that is a problem and
Yes.
needs an explanation. And so
Right.
that's one reason we were interested in this area as well.
Okay.
So here's a geologic map of that area. I showed this last time as well. And this is sort of the main part of the Chugach Prince William Terrane, or the terrane. This is like the thickest section. The red dashed line is the Border Ranges Fault, and that separates the Chugach Prince William Terrane, as well as the Yakutat, which is this guy over here,
Mm.
from the rest of North America.
Yeah.
And so like the stuff you're going to be working on, Nick, I believe is the Talkeetna Arc, which is up in this part of the world, for example. So it's south of that.
Thank you.
And then that cross section A prime, I want to show that because that sort of shows you the third dimension and also shows the plutons schematically. This is just schematic.
Hmm.
And I stole this from George Plafker's seminal 1994 paper. So this shows the Chugach, there's the Border Ranges Fault right there. So this is the rest of North America. Here's the Valdez group. So the Cretaceous portion of the Chugach Terrane is the Valdez group. The Prince William Terrane is the Orca group. And you can see all these plutons have intruded into this accretionary wedge complex.
Hmm.
And I guess that's all I need to. Oh, and some of the work that we've been showing, I showed this last time, is that
Yeah.
it ranges in age from, latest Cretaceous and some pretty young components too. All right, so that's the Chugach Prince William Terrane. And again, just wanted to show you they are gorgeous turbidites, these interbedded sandstones and shales.
My goodness.
And so now let's come back to the plutons, which I really wanted to focus, and that was the point of today's discussion.
Good.
So the Chugach Prince William Terrane is here in green, and intruded into it are these red blobs, which is the Sanic-Baranoff plutons. And these things range in age from about 63 million years out here on Sanic Island all the way down to 47 million years here on Baranoff. And notice they young systematically, especially here in the west.
Mm.
Kind of starts to fall apart here in the east. And I mentioned this last time. We just published a paper in 2024 where all these dates are there. And we talk about a sort of a tale of two belts, the western belt and the eastern belt. And in one pluton, in fact, here on Baranoff Island, this is the Crawfish Inlet pluton I'm circling right there.
Hmm.
We have ages ranging from 47 to 53 million years. So this is a composite pluton where you had, igneous rocks being injected, filling up this space over a period of 6 to 7 million years. And so that's why you get those ranges of ages.
Hmm.
And I'll come back to this because this actually turns out to be a really interesting part of the story. Okay, so let's see what these things look like. Any tectonic model for the Chugach Prince William Terrane and for these Sanic-Baranoff plutons must explain that we have an accretionary, how do we have this accretionary wedge intruded by plutons? Because that's weird, as I pointed out in that cartoon.
Yes.
And also, why do we have this younging from west to east? Those are the big questions. So just to show you what these things look like, here's a couple or an example from the Nagai Island Pluton, a couple students collecting samples there. They're gorgeous granites that intrude these things. If you plot up their chemistries, they're mostly granite. You can see here on the left, there are some tonalite granodiorite compositions. And perhaps more importantly, they're all paraluminous, meaning that they're high in aluminum.
Yes.
And the best way to do that for these types of igneous rocks is you melt in some sediment because those are high in aluminum and that jacks up the aluminum content. And, turbidites are perfect for this because they're interbedded sands and shales are full of aluminum.
Hmm.
So this suggests that, yes, you probably have some mantle melts coming in, but you're mixing in sedimentary material, making these things paraluminous.
Hmm.
The idea. And that is reinforced by the photomicrographs. So here's a photomicrograph from the Nagai Island Pluton. These are thin sections. There's the scale bar right there. On the left is plane polarized light. On the right is cross polarized light. And what you find are these xenocrysts of metamorphic minerals, in this case, andalusite, just
Hmm.
floating in these granites, and it's pretty cool because when you walk across these, you see these like knots and you go, aha, I wonder if that's a xenolith. So we purposely collect them,
Ah.
or a xenocryst. Um, and sure enough, this is andalusite. And this actually turns out to be important because it suggests if these xenocrysts are inherited from the wall rocks
Okay.
where you're creating these granites, like they're being ripped off and you're mixing them in with mantle melts, then it suggests that the accretionary wedge here is pretty and not very thick
Oh.
because to have andalusite, you need depths of 12 kilometers maximum. Otherwise, it's no longer stable or something thinner.
Hmm.
So, and I'm pointing this out here because if you go further west to like Prince William Sound area, this is the Hive Island and Alec Plutons. There we see kyanite xenocrysts, which means probably the wedge is much thicker. And even in map view, you see that, right? You see that much more turbidites are in that area. And this sort of reinforces it. So these are just spectacular. This is almost the entire thin section. And here you're getting these really beautiful reaction textures of corundum and hercynite. That's what those stand for, replacing kyanite. So these incredible reaction textures. And I just can't help myself because I used to be a metamorphic petrologist. Zooming in on this area, and you
Good.
can see the hercynitic spinel. This is a spinel that's aluminum rich, and also a corundum replacing the kyanite. Anyway, super cool.
Like, Cam, can you stop your share for a sec? So
Yeah. Oh, yeah.
I want to pause, make sure I'm hearing a few things at this point in the story. And viewers, I enjoyed the visit with Cameron so much last week, and it was so me jumping in so much, and like, let's stop and talk. And then he's like, "Come on, man, I got like 60 slides."
Yeah.
So
Yeah,
I'm
that's no
trying to be
problem.
a little bit more laying back in the weeds, but we do want to go back and forth a little bit at least. So, am I hearing right now that we have variable thickness of the accretionary wedge and the turbidites? We're acquiring that sediment at the same time that some of these plutons are coming in. So you're using those metamorphic rocks to kind of realize it's not just this thick wad of turbidites all along the margin that are then getting shot full of plutons.
Yes, I think you're exactly right. I think what it's
Okay.
showing is that you have variable thickness of this accretionary wedge complex. And in the area, like near Anchorage in Prince William Sound area, that's where the thickest blah is in there. And this will come out a little later too, I think, in some of the isotopic compositions that we see in these plutons as well, which is
So
kind of, I'll show those data.
So you've got two things going on essentially at the same time, roughly in this time window that we're acquiring sediment in a subduction zone and we're doing this near trench magma stuff and we're heading towards a tectonic model that you must have. And,
Yep.
and I'll be curious to see if that tectonic model has changed over the last 15 years. But I'm just checking in to make sure that we're all together. I think we are. So
Yep. You got
let's
it.
go right back to the slides. Great job. Let's keep it going. Love
Sounds
it.
good. Let's see here. Share.
Yep, got it. Okay.
Is it look good for you guys?
It sure does.
Okay, good. I got all kinds of stuff in my way. Okay, there we go. Now I can see
Okay,
it.
good.
Okay, good. So let's see. I gotta click, I guess. There we go. Yeah, that was the last slide. So
Good.
this is a summary of, this is a really busy slide. I
This is
apologize.
great. This is great.
Let me walk you through it. So here's the time scale on the left,
Good.
and here's going from west to east.
Yeah.
For different regions along the accretionary wedge. And the things in green and blue, I guess, are the sedimentary rocks. These are the
Mm-hmm.
turbidites and then associated melanges, which we talked a little bit about last time.
Mm-hmm.
And then the red bars are the ages of the plutons that are intruding these rocks.
Yes.
And so, to your point, Nick, that you just made, in the West, the plutons are considerably younger than any of the things we dated.
Yeah.
So they came in after. But in the Prince William Sound area, you had deposition of these turbidites before and after, and probably during the
Huh.
intrusion of these plutons, because
Huh.
they're 56 to 54 million years ago. And then I just have to highlight this one bar right here, which is the so-called resurrection ophiolite, which are also placed in these rocks at that same time. So they're coeval, this ophiolite complex, with the intrusion of these plutons, and that has to figure into our model as well. And I'll do that a little bit later.
And the blue schist that you mentioned last week, that's way off this. This is way
Yeah,
down
that's
below. That's
much
done.
older, much
Yeah.
older. Yeah, so that's not part of the story
Okay.
exactly.
Thank
Yep.
you.
And so then, yeah, here, so you can see the systematic younging, and Yakutat, those are the ages of the plutons. And again, there's overlap with intrusion. And in this case, they're upgraded to schists, these
Hmm.
sediments. So it's called the schist of Nunatak Fjord, but it's Chugach Prince William rocks is how we interpret it.
Okay.
And then here's that range of ages on the Crawfish Inlet Pluton over on Baranof Island in the extreme east.
Huh.
Okay,
Okay. Good.
so oh yeah, I just threw this in there at the last minute. So just to show you, hey, yeah, there are these ophiolites. This is in Resurrection Bay. You should go there if you get a chance to go to Seward. It's
Hmm.
a great ride on a boat and beautiful pillow basalts. Just gorgeous. There's sheeted dikes too in places. So it looks like an ophiolite.
Hmm.
And then the question is like, what's the tectonic setting for this ophiolite? It's probably not a normal mid-ocean ridge is what we would argue.
Mm-hmm.
All right. So now let's go to some of the isotopic data. And I was telling you, Nick, about this a little bit earlier.
Good.
So one of the things you do is you date these zircons, you get the ages using uranium lead, and that's the x-axis on this diagram. So those are the ages. But it's for a little bit more money, you can actually get the hafnium isotopic signature of these zircons as well. And that tells you a little bit about the source material that's making up these plutons. And it's the epsilon notation is just you're taking this ratio of these two isotopes of hafnium, one's radiogenic, the other is stable, and you're just normalizing it to a standard. And the standard we normalize it to is called CHUR, which is chondrite uniform reservoir. This is just bulk earth composition,
Okay.
right?
Yep.
And that's why that's at 0, because we're
Mhm.
normalizing these data to that. Otherwise, they're crazy numbers, and it's hard to keep your brain around them. And the other line on here is this depleted mantle. And so if you were to remove material from the mantle let's point to this diagram, at 65 million years ago, which is over here,
Yep.
then the composition of that material that you just removed from the mantle, a basalt, let's say, would be around plus 15 epsilon hafnium ratio,
Mhm.
because that's the signature of the depleted mantle at that time.
Okay.
And you can see that this ratio doesn't change much over, short periods of geologic time from 45 million years to 65 million years. It's a slowly changing ratio, and that's why that line looks flat.
Mm-hmm.
So the cool part is that so we did this for our plutons, and one of the things that you notice, hopefully right away, so on the left are all the data. On the right are the averages of those data.
Thank you.
And one of the things I think hopefully jumps out at you, I got to minimize our faces. There we go. Now I can see it all. Is this change there we go, of where the older plutons are somewhat what we would call primitive, meaning they just came out of the mantle not very long ago,
Yeah.
or mixing at least with sediments that didn't come out of the mantle very long ago. So very juvenile type material. And then it gets more what we call evolved. So there must be some older crusts getting involved here. And this is like right around that thick section in the Prince William
Right.
Sound.
Right.
But also on Baranof too, because some of these data are from Baranof. And then they get primitive again. In fact, it goes back to essentially a mantle signature with no old crust whatsoever.
Wow.
And when we first got these data, we're like, okay, what's going on here?
Uh-huh.
And I presented some of this to people at the Arizona Laser Crown Center, including George Garrels. And George was the one who right away said, well, maybe it's just reflecting what you're melting into these rocks to give you the granites, the sediments. Maybe that's just the isotopic signature of the sediments.
Mm-hmm.
And luckily, we had been collecting those data. And here's just an example graph of those kinds of data. So these are the hafnium isotope signatures of the detrital zircons from across the CPW. This is kind of an older slide. We have a lot more data now.
Mm-hmm.
And so it's like, oh, good, we have those data. And so I'm going to show them in a slightly different way, which is here. And these are probability distribution plots of the hafnium isotope turbidite data. So this is taking those detrital zircons and saying, okay, this is the isotopic signature of the turbidites. This would be the material that you're melting into those mantle melts to form these granites.
Mm-hmm.
And the averages are shown by these little stars for the different areas. So notice as you go from west to east, so these are the older plutons to the younger plutons, so west to east, there does appear to be a difference, a change. And things do look more evolved over in here compared to over in here. And so it's like, oh, and in fact, if you superimpose the Pluton data, which is this, it's like, oh yeah, it tracks pretty well. So that's a good explanation for most of that trend, at least the downward trend, going from more primitive to more evolved. But then this incredible, upward swing and that's all on Baranoff. That's all within this one Pluton,
Yeah.
the Crawfish Inlet Pluton. What is going on? So as these youngest Plutons appear to have this much more primitive signature. So that was kind of interesting.
Yes.
So that takes me to the models.
Yeah, we're building to this. I can feel it, man. I can feel it. I love it.
So what about these plutons? And notice, and I'm not going to go through all these, but notice, a flurry of activity back in the 70s, kind of right on the heels of plate tectonics, which is kind of cool. Because people recognize, like, what are these plutons doing in the forearc, in front of the arc? And so people were proposing these different models, and everyone's kind of settled on number 4. So you look at anything in the literature since then, and everyone sort of points to ridge subduction. And that's kind of the easiest and best way to get heat. I mean, that's the problem. You got to get heat into the forearc in order to partially melt those rocks and to make plutons and all that kind of stuff. So that's why people have really pointed at number 4. And just to show you what that kind of looks like, this is from a paper by Dwight Bradley and others back in 2003. And this shows you what ridge subduction looks like. So here's a subduction zone over here with my pointer. There's a ridge, and then here's a subduction zone. So you're taking this ridge and you're subducting it. And we call that a TRT, or trench, ridge, trench boundary.
Thank you.
So this is that trench, ridge, trench boundary. You're subducting it. And notice, this is a great way, you got upwelling mantle. This is a great way to get heat and melts into the forearc. There's the modern arc back there. And so this is how you could create those plutons. So there have been 2 sort of dominant models for explaining these Sanic-Baranoff plutons. One was published by Peter Heusler back in 2003, and this is the so-called northern option. And so here's the Sanic-Baranoff pluton, the Chugach Prince William terrane shown here in green. And you're seeing plate boundaries between, Farallon and Kula plate. And in order to explain the plutons, or how do you get a trench up in Alaska, what they did is said, we need another plate. Everyone agrees that there was a Kula and Farallon plate, and that boundary was subducting somewhere, or that ridge, somewhere here in the Pacific Northwest. That one everyone agrees with. But in order to explain this sort of time transgressive nature of the plutons up here, you need another plate. And especially if, subducted at that angle, notice that ridge would sweep along the margin as you consume this plate. That make sense?
Yes, it does.
So the other option is the fixed TRT boundary. That is the southern option. It said, well, no, we don't believe in a resurrection plate. And at the time, this wasn't even suggested. This was sort of the accepted model. And Darrell Cowan in 1982 first published this, saying, well, maybe what happened is that we moved the Chugach Prince William terrane over this boundary and moved it up to Alaska where we see it today. And then he republished it coincidentally the same year as Heusler et al., reinforcing that model with a lot more new data and things like that. So this is actually what got John and I started originally. It was like, we're going to test these 2 models. that was one of the ideas. Another model, but it's just a variation on a theme. This was published by us in 2017. Is yes, we have a trench subduction. Here's the subduction zone right here. But perhaps the Chugach Prince William terrane and the intrusion of these plutons happened in some sort of supra-subduction zone setting.
Hmm.
And so here's this cross section here. So here's the subduction of that downgoing slab. You open up a slab window here, thanks to the subduction of this trench.
Mm-hmm.
That would provide heat to the forearc in this area. It would also provide the melts for the ophiolite. So that's the pillow basalts I'm pointing out right there in the resurrection ophiolite. But then you also are partially melting the base of this thing because you're bringing in all that heat. And that's the Sanok-Baranov plutons intruding at the same time.
Okay.
And of course, you're still dumping in sediment here at the same time too. So that's kind of our model of how these things form. And I showed this last time, and this was not what I want to do now is take us to the translation model, saying,
Good.
okay, well, where did this happen? and the idea is like we think it happened in the Pacific Northwest. And so that's what I want to do here.
Yeah, before we go there, Cam, let's stop your share again.
Okay.
Couple of things.
I threw a lot of stuff. Sorry.
No, this is perfect. Come on, man. This is perfect. So personally, we both went to the University of Wisconsin in the 1980s. We both graduated with a bachelor's degree in geology from Madison in 1986. I went to Idaho State for graduate school. I think you went to Princeton.
Yep.
All right. So that tells you what kind of students we were back in Madison, how different we were. The point is, I don't remember anybody talking about Baja, BC or translation to the north or anything like that. So when I started showing up in Pocatello, that was Paul Link and others who were like this paleomagnetic stuff and this movement north. It was so anti any kind of translation that it wasn't until I moved up here to Ellensburg, and Mount Stewart is just to the north of my campus, that I slowly kind of got myself into this world. That got me to Daryl Cowan. That got me to this other stuff, and I've been really heavily into this. Would you mind just briefly sharing, even maybe when you started working with Garver, who was a Daryl Cowan student, were you not super into the translation stuff? And have you kind of changed your view as you've been working with John over the years?
Completely. Yeah, John's had a strong influence on that because I actually did publish a paper back in, I can't even remember the date, late 90s or early 2000s.
Okay.
On the Extall pluton actually in British Columbia, but just south of Southeast Alaska, up near Prince Rupert. And the Extall was one of these plutons that was showing shallow inclinations. And it was like, huh. And so we came up with a very convoluted story to explain those, that it was a type of fault bend folding where you actually folded these plutons because there was steep. That was the thing about that pluton. There were steep directions and there were shallow directions.
Okay.
So we said, well, you took the steep directions and folded them to be the shallow directions. That's the explanation.
Okay. Yeah.
But since then, actually, Link Hollister, who was my PhD advisor, and so this was after I was working with him, he hated this idea. and he said, no, this stuff is coming from down south. I'm like, well, I don't know. Bob's pretty convincing too, because I'd been starting to work with Bob Butler. He was the paleomag guy, and he wanted everything to be, some movement for sure, but not from California.
Right.
And so... but he showed Klink, and then a student of his showed that it looks like you actually reset these paleomag directions. And that's why you have both shallow and steep, is that the shallow ones that were all the way through the Pluton got reset to steep where they are today because of bringing up what's called the Coast Plutonic Complex in this big shear zone. And it's, you're sticking a hot iron right there, and now you can reset all of those directions. So I'm like, okay. And now that I've been working with John, I've seen the light, or some people will say I've drank the Kool-Aid, but we'll see.
Well, that's ultimately, I'm not pushing intensely for this with every last person, but I think it is important to show um, over the, if you've been thinking about stuff for a while, staying open to having conversations with others, collaborating with others. Boy, it does seem like some can allow themselves to change their general points of view along the Western margin, and so stories like yours, I think, are important to point out.
And, and
Okay,
and I think, like you
yeah,
said, it always bugged me that you had to ignore the paleomag data.
yeah,
That was, you just had to like separate that and say,
yeah,
well, I don't know why all those data are so consistent. And now you don't have to, is what
good.
I'm.
Good. Thank you for that interlude. Let's go
Sure.
back. I can feel us building towards a couple of landing points here,
Yeah,
but
we're
this is
almost there, actually.
okay. Good.
I don't have much more. Okay, I think that you're seeing everything, I assume.
We got it again. You bet.
Okay, so I showed this slide last week, and this is where I tried to make the case that the Chugach Prince William Terrane, which is up here in green with that hatchard, and the Yakutat Terrane was down here in the Pacific Northwest. And this is the geologic evidence, or actually just part of the geologic evidence that really makes that connection.
Hmm.
So I won't show that again, but let's go look at the Pacific Northwest. So here's a map of that area. Here's the Western Melange Belt. So that last slide, maybe I'll just go back. This is where we tried to make a connection between the Nanaimo,
Yeah.
Western Melange Belt, and the Yakutat Terrane.
Wow. Love
So
it.
there's the Yakutat up there. And if we go to
Yes.
the Pacific Northwest, here's the Nanaimo in green. Here's the Western Melange Belt in green. And what's interesting is that this margin is kind of a truncated margin. I mean, you have this big fault system here called the Totino Fault here. Then this margin here is buried under glacial stuff, but it separates these crescent basalts. These are Eocene age basalts of the so-called Silesia terrane that's been accreted onto the margin pretty recently from the rest of the things. And so it's like, okay, well, here's this stuff that wasn't there when all this stuff was going on. So
Right.
let's put Yakutat there because it appears to be related to the Western Melange Belt and the Nanaimo. And so
Huh.
that's what this slide does. We slide all that stuff down. There's the Yakutat Terrane, and there's two parts of it, this Yak A and Yak B, and that's shown over here on the right. And what we're showing here is these are two basement terranes. The older basement are this is these flishes and melange units, mostly Cretaceous. Don't have time to develop that.
Yeah.
But then they're in fault contact with these Eocene basalts, and that's the basement. And there's a big old unconformity here where you're depositing these younger sediments up here on top.
Huh.
And so that's these two basement terranes. And we would argue that this Eocene basalts and also Silesia, which is on this side, formed in some sort of over thickened, oceanic plateau here along this ridge. And then these basalts were shoved underneath the Yakutat A terrane, which are these flishes that have these characteristic Precambrian zircon ages that are just identical with the Melange Belt.
Mm-hmm.
So let me go to the next slide. So that's the slide on your left, and notice the timestamps around 55 million years ago. So this is that over-thickened oceanic lithosphere. This half gets shoved under what will be the Yakutat terrane and starts to excise it and move it north. This size is Silesia, and it gets shoved into that area, where we find it, where they're called the crescent basalts and things like that today.
Mm-hmm.
And that's showing it here. And then we accrete Silesia at that time. And there goes Yakutat heading to the north. Does that make sense? Did I go too fast?
No, this stuff in the last 5 minutes is quite familiar to us. We have been
Yeah.
thinking about Silesia and the Western Melange Belt in the last couple of winters with programs, but what's new to
Yeah,
me,
like
Cam,
Erin Donahue,
yes,
this was her PhD essentially.
yes.
Yeah.
What's new
Yep.
to me is that the Chugach is heading north as well with the Yakutat. I think you were saying that at least a week ago. Are you saying that again today? Where's the
Chugach.
Chugach on these maps? Well,
So it's
there it is.
north of
Okay.
the Yakutat. So I think
Yeah.
everyone agrees that you have to restore it to the south, and we would
Right.
say this is one continuous belt.
Ha.
Yeah.
Okay.
Yeah.
Okay.
And it's in this area where you're making, you're bringing in those ophiolites. That's that complicated diagram of subducting, oceanic lithosphere, and now you're subducting this over thickened stuff, and you have
Mhm.
extension in the forearc forming these ophiolites and the Sanic Baronoff plutons. So it just all hell broke loose in this area back there.
Yes. Well, I have a feeling that we're landing back with your stray plots that are heading back towards mantle stuff again. Am I feeling that correctly?
Yes, yes, and we're
Okay,
almost there. I wanted to show you what we think is the translation history, and then we'll
good.
come back to those mantle contributions of the Sanic Baronoff plutons.
Beautiful.
So here's, I think I showed this before. Yeah, and so there's Chugach, Prince William, and Yakutat. That's A and B, and we think I tried to show, and that was last week too, that A and B was down here by C. And
Yeah.
now I want to do a real stretch and take all of that material and put it down here by D, and focus on these Polona, Orocopia, Rand schists. I know you've had people on talk about these too, but I just want to show those same data and compare them to ours. So
Good.
there's the Polona, Orocopia, Rand. These are detrital zircons from that area. They have these characteristic Precambrian peaks. Here's our data from the Yakutat group. And, I'm sorry, they just look very much the same. So it's based on this geologic evidence that we'd say we want those down there.
Hmm.
And so this is our reconstruction, and we put this in our 2015 paper. We said, all right, there's the Chugach Prince William terrain. That's the stuff we've been working on in green.
Yeah. Yeah.
There's the insular terrain, or the Wrangellia composite terrain, whatever you want to call it.
Right.
And it needs to be down here in Southern California.
Huh.
And so now I'm just going to walk you through our reconstruction, and then that's that same unit here, Chugach with the insular terrain. And all those dots are the paleomag that you were talking about. These are these long-standing paleomag data. And this diagram is honoring those data. So we're saying, okay, that's where those things should be. And so it fits together really nicely. And now, so that's at 70 million years. Notice there's a timestamp here. And I'm just going to bring this along the margin. And by 50 to 45 million years, and we can argue over the exact times, it's at this point in the Pacific Northwest. And there's Yakutat for you. And this is when all sort of hell broke loose and you subducted that ridge.
Yeah.
And then we keep going. And now there goes Chugach, Prince William terrain and Yakutat. And by 35, probably around 35 million years, Yakutat breaks free and it starts heading north to where it's colliding today with North America, giving you the Fairweather Mountains, or
Yeah.
the Chugach Mountains and Fairweather Peak and all those. And again, that's honoring all the paleomag, that reconstruction.
Yes.
So this is more or less my last slide.
Okay.
This takes us back to that 50 million year time period.
Yeah.
And I just wanted to point out that back, in Wells et al. Back in 2014, published this figure, and they said too that Yakutat, the basement of Yakutat, the basaltic basement, is probably the same as Silesia. Here's that mid-ocean ridge, and that went north. Silesia got accreted, but what I love about this figure, they also put the location of the Yellowstone hotspot from 56 million years to 50 million years. So it looks like the Yellowstone hotspot was right in this area at this same time. And so as soon as we started getting these hafnium data from the Sanic Baronoff plutons, that's this guy, we're like, well, maybe that's what we're seeing in the Crawfish Inlet pluton.
There we
Is
go.
that's the Yellowstone hotspot
Yeah.
driving the isotopic signature, where now you're taking stuff right out of the mantle. And that's what we're seeing. And that was that departure, remember, from just reflecting the sediments. So that's it. That's all I have.
We made it home. We made it home. Please stop your share. I got a couple final thoughts that I'd like to go back and forth with you on. It's a pleasure. It's a pleasure to chat with you after all these years. Thank you for that. Number two, I thought it was going to be hard work for me to work in Alaska and basically go to this unknown state to me geologically and try to start from scratch. I'm not starting from scratch because half of this shit was made down here. Like, I mean, I just,
That's right.
I even talking to the Talkeetna Arc, I did a program the other day, and the gentleman's like, well, the Peninsula Ranges has got a very similar story to Vancouver Island, and I'm like, holy
Like, oh
cow!
my
Like,
gosh. Yep.
so
Yep.
so that is so pleasing to me, and I'm just going to lean pretty hard into that. I think the third thing is just last winter, Cam, I was looking at the Cascades and I wanted to start earlier than the Cascades. And I had Jeff Tepper, a geochemist from
Yep.
University of
Great
Puget
place.
Sound,
Yep.
uh, having 46 million years ago as the initiation of the subduction zone to make the Cascade Volcanic Arc. But I wanted to do a bunch of episodes prior to that. And what were we doing? Here in Washington today, we were talking about the Western Melange. We were talking about the ugly Russell Ranch at White Pass in Washington with magmas coming up through. And before I knew it, we were into debates about migrating triple junction. I was using a green M&M and putting it on the map, and Mike Eddy was having one model, and Jeff Tepper was having another. And here's the same kind, literally the same Arcosic sandstone, the
Yep.
Western Melange that's being invaded from below before the Cascades get started. So even that has this echo up there. I mean, this
It's
is
amazing. Yeah.
wild to me.
Yeah.
Maybe we can finish with, if you're feeling comfortable, have you been in the crosshairs with this model and this vitriol and this absolute, like even 15 years ago, like absolutely not. There's no way this stuff is from Washington, let alone Southern California.
No, I think it's mellowed. I think it's people are trying to, now that there's more and more data, I think people are really trying to come up with reconciling all these data. And I think, especially after Bernie Hausen's work on that paper with Basil, where he revisited all the paleomag, it's like, this is solid.
Huh.
And so I think people are finally coming around to saying we need to reconcile all this. And maybe it's not all the way to Southern California, but this is where, and I just don't have the capacity to do this, but I would love to start putting these little bits and pieces into something like G plates and try to make, which is this plate reconstruction program.
Yeah.
I mean, that's just asking to be done. And
Huh.
I hope someone does it and uses all these different geologic constraints and say, okay, this is a super complicated jigsaw puzzle. And with what we know about plate motions, what's possible? And then we can
Yes.
eliminate some of the complexity, maybe. But yeah.
Let's finish personally. I'm hoping to continue to teach and just keep doing these kinds of programs. We're the same vintage. Are you still scheming about new research angles, or are you kind of doing mostly teaching these days and not doing as much work up in Alaska?
Well, our grant did run out and we didn't re-up. And my wife is retired, which is one thing.
Yeah,
But I don't see myself turning off my brain. I mean,
yeah,
I want to keep going. I'll be teaching probably for another at least 5 years, and we always have undergraduate theses because they're required at Carleton.
yeah.
So I hope to be going back up to Alaska and
Good.
working out some of the minor details. Like I've never really been west of the Ialic Peninsula, which is down near the Seward area. There's a bunch of these Sanic Baranoff plutons in there. It's just really hard to get to.
Yeah.
And I would love to go there. We'll
Ha,
see.
nice. Well, Dr. Cameron Davidson from Carleton College, thank you again for your time. Please hold the line. I'll stop the recording. We can chat for another couple minutes, but thanks again for your time today, Cam.
Well, thank you, Nick.